3.3, number 49 and 52. I got stuck.
Let's see, 49. Oh, okay, this is good. There's kind of a big idea that I left untalked about.
I got this one.
Okay,
This
let's
one, yeah.
catch up. So, when we developed the formula for the derivative of sine, part of what we looked at to be able to do that was this limit.
Yes.
Does anyone remember what that limit was? We'll investigate it with a table. Later this semester, we'll actually develop something using derivatives that'll make this really easy. And we'll look back at all the limits of the coming easy. Finally. Yeah, this limit was 1. So I really want to analyze what this says. The limit of the sine of an angle divided by that angle as it goes to 1, as it goes to 0 is 1. We say that again. The limit of the sine of an angle divided by that angle. Are you guys with me?
Mm-hmm.
That goes to 1 as x goes to 0, as the angle goes to 0. So what's wrong with this question? Why is that not just 1?
Because it's the angle is in times.
The angles.
The angle is times.
Don't agree.
More than.
The rule says it's 1 if you have the same angle. And don't get me wrong, I need you to understand. Very often we'll get, very quick side note. Do you guys happen to remember the double angle formula for sine?
Oh,
where the shit are you? Anybody remember that one?
Hold on.
2 sine x cosine x. So when I ask people what sine 4x, they understandably would say 4 sine x cosine x. And that, of course, is wrong, because the heart of the formula is, if I have double an angle, it's twice sine of that angle cosine of the angle. So when I see this, I think, what is that double of? That's double 2x. So it should actually be 2 sine 2x cosine 2x. So on one level, when we learn stuff like identities, when we learn equations, when we learn formulas, we have to understand what it's trying to tell me, what it requires. What does this require? It requires the sine and the bottom to have the same angle that they're talking about. So what am I missing on the second dude, obviously?
A 4.
On the bottom.
If only I was allowed to do something so I could put a 4 in the bottom. I can multiply top and bottom by 4,
No,
yes?
Get the 4 up,
You guys with me? That, ooh, wow, that's grammar. Now, so what's this limit then, by definition?
yeah.
That's 1 times, so this is 4.
Oh, because you made them the same.
Yes! So there's a whole little section, which section is that, Sarah? In the homework in section
3.3.
3.3, that references this little fact, right? The next thing I want you to realize is, just in case they give you a problem like this, if the limit of sine of x over x is 1, what do you think the limit of x over sine x is? No. Still 1, because it just flipped, right? Still 1. You guys see that?
Yeah.
Yes.
So what if it was sine 6x over 6 or over x?
Oh, it'd just be the same. I would multiply by 6 in the top.
What about what you did over on the right?
Say again, sorry.
Like to the right. When you plug in the 4. Yeah.
Oh.
What if it was 6x?
Alright, what if it's 6x? Alright, the formula says if I have double an angle, it's twice sine of that angle cosine of the angle. So what am I doubling? So it'll be 2 sine 3x cosine 3x. That's why we call it the double angle formula. So you think, what am I doubling? That's what I rewrite it in terms of. But again, I want you to get my broader point. It is unbelievably understandable somebody would do that. Put the 4 there. Because as a student, you're like, I'm not exactly sure what that's trying to tell me. I just see a 2 and a 2, so that seems to go together. Well, the important thing is, when the angle is doubled, I can make it twice sine of that angle that was doubled, blah, 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 right? So I need you to understand, I completely get a misinterpretation. So that's why I want this to be really clear. This is not that huge of a deal. It's actually kind of cool. I want you to understand what this means. When x gets really close to 0, what must be true about these two things in order for the ratio to become 1?
They're equals.
Those two things have to be really close. Does the limit ever get to 1?
No.
Because it's a limit, it never gets there. But real quick, can somebody have their calculator? Make sure you're in radians. What is sine of 0.07? Make sure you're in radians.
0.0699.
0.0699, and for any human, how would you round that number?
428,473.
Sarah's gonna keep going. We'll check it with her tomorrow.
0.07.
Yes! You guys with me? Is that exactly equal, is it? We don't give a shit because we know the limit is 1, so it's never quite 1. But aren't these damn close? The smaller the angle gets, the closer sine gets to just equal the angle. We use that fact in physics all the time. If I have a pendulum and I don't swing it very much, I can approximate the angle to be equal to just how much I swung it by. It's kind of nice. It's stupid. Anyway, I'll stop. So that's a beautiful little thing that comes out of this. I'm not going to harp on this too much. Those problems become. Let me ask you this. One last problem related to this. What if they gave me sine 7x over sine 3x? Can anyone identify? This one's really bad. It's missing a lot of shit. What does the sine 7x need on its bottom to work?
That's
It needs 7x, correct? So let me make some room here. So this guy needs something on the bottom, and this guy needs something on the top, correct?
Yeah.
Yes, so this guy needs a 3x on the top, so what do I better at the same time do? No. Didn't I just put a 3x there that wasn't there? How do I make that actually legal? There, now it's legal, correct? I did top and bottom by 3x. What does this guy need here? 7x, so what do I better do at the same time? On the top. So what is this, what's this limit? 1. What's this limit? 1. What do the x's do? Cancel. So what do I get? 7/3. Yeah, cool, alright. And again, it's just a recognition of something that we did before. We proved this, and then we realized, oh, if it's sine of something divided by that same thing, the limit as x goes to 0 is 1. So then we can kind of play with it. So this is not a huge deal, but it is sort of like building the idea of how we can play with shit. If I know this, I can play with it. I can make it look like that, and then I can use it. Okay, maybe. Yes?
I just wanted to check, is this right then?
Oh, I don't know. Ask me later, sir. I'm sorry. Sorry?
The last problem was about.
This guy.
Yes.
So I introduced, something I could start using is different colors. What would they be? Why are you so get thick? Yeah. Okay. This and this, yes? That made it legal. I just multiply by 1, correct? If I do the top and the bottom, I multiply by 1. I can do that anytime I want to, yes? What's the one time I'm not allowed to multiply top and bottom by 7x? If x is 0. And is x ever 0 in this problem? No, because I'm letting you approach 0. We never get to 0. Okay, good. And then what did I do here? I put a 3x on the top, but I also divided by 3x. So didn't I just multiply by 1 again? I could do that all day long. Yes? We can change the look of, where do we use that the most? Fractions. So that we can combine them. We change what they look like so we're able to combine them. Okay. Moving on. It's not a huge deal, but it is kind of a nifty little concept. What did I do? Okay. Anything else before I move on? Yes?
3.5, number 67.
Oh, yeah. Okay.
Uh-oh.
Sorry.
Never worried.
This one here, let me see, it's coming. Come on, little dude. There we go. That one?
Yep. Sorry about that.
Oh, shite.
That's all my fault.
Oh, good.
Came out wrong.
67 on 3.5. Does anyone try that one out yet?
Okay, that's fine.
No.
By the way, I need this to be understood. Okay.
It's freaking hard.
Yeah, you can kind of tell. It's the last problem in the section. It's got a freaking ellipse in it. You know, so you're like, okay, this might be a little bit tough. So I want you to try this problem. Do as much as you can with it. It is kind of freaky. I will just say that. But I have this feeling that not a lot of us have tried this yet. So I'm not going to say too much about it. So let's just see if we can understand what it's trying to ask us. So it's got a lamp, 3 units to the right of the y-axis. You guys see that?
Mm-hmm.
So even though the lamp pole is a little further, the lamp is at 3. You guys agree with me?
Mhm.
And the shadow created by, there's some kind of an elliptical thing. There's like a little UFO there that's blocking the light, so it's making that shadow. You with me?
Mhm.
Okay. If the point -5, 0 is on the edge of the shadow, how far above the x-axis is the lamp located? You would like that, Jeff. By the way, so what do you think? Do you guys see how this point here might be interesting? Because what is this line?
The tangent of that.
Alright, that's awesome. Yeah, we're trying to. So. And again, yeah, guys, I need you to understand. I love you. There's some of you guys don't do any of the homework. And then the rest of you guys are like, if you don't do every single problem perfect, you think you're the worst person in the world. I'm like, the truth is in the middle, okay? So this problem is meant to challenge you. So if you can't finish it, it's not the end of the world. This is a freaky little problem. It is. But I need you to try to get used to not immediately knowing how to do something. Am I going to put a problem like this in the test? Of course not.
Please don't. Okay.
I would put something like that as a
Like,
bonus. Yeah.
no.
Okay. This is a difficult problem, but I'm not going to say too much. If not, a lot of people have tried it, and I don't see a lot of recognition happening. So, more of you give it a try, and then we'll see. Okay. So, do you guys see fundamentally what it's asking? It wants to know how far above the x-axis this light is. Do you guys see it's all about this line? If you knew what this line was, couldn't you figure out what that was? You would just plug a 3 in. You see what I'm saying? So I've given you the way to look at this. Okay. So again, I gotta tell you something. I haven't looked at this problem in years. So when I first saw this, I'm like, I don't know how to do this shit. So as I was talking to you, I was like, oh, okay. But the thing to realize is, they told me that line must be important because it connects the thing they're talking to me about to the thing they referenced. Oh, look, you know this point. Okay, that's important. And it connects to the freaking light. So that must be important. So then I thought, okay, what's calculus about that? Because we're calculus. And it's like, oh, it's a tangent line. Okay.
So
Yeah, but you don't know the
I know, but at least you know what to start trying to do. You know the function, don't you?
Yeah. But that doesn't reach all the way.
What do you need to get the tangent line? You need to take this guy's derivative. I agree with you. Do you know what point this is? Do you know what point this is? No. No, you don't. Sorry. That excites me. It's kind of like, oh shit, I gotta work at this weird. I can't just plug shit in and get the answer. But at least you kind of know. The important thing is the physical relationship. What's going on? What's the calculus involved in this problem? How do I even start to attack this problem? Now, everybody should at least know how to start to attack this problem. Yes?
Isn't this problem also kind of like the one you do with Craig?
In some way, I guess, maybe. It definitely would involve the calculus you need. Yeah, you could maybe see some triangles in this. So if you had some other information, you could possibly use trig. But we don't have enough information for trig.
Oh, okay. Alright.
But I see what you're thinking, because there are right triangles involved, right? But
Yeah.
we don't have enough information for trig, yeah. Poor little trig's like, it's out of my pay grade. Alright, maybe. So again, dear God, I need you to understand, if that's the only problem you had trouble with, holy shit, you're doing amazing. So anything else before we move on? Okay. That is a weird ass problem. It just is. But I'm gonna
Thanks
give you
for
some of
helping
those.
us feel better.
Huh?
I said, thank
No, I
you for
mean,
helping us
I'm
feel
not
better.
gonna just, put smoke in your ass. There's a good reason that you have trouble with this problem. It's not immediately obvious. Okay. So, let me remind you what we've done. We already talked about implicit. We had a little quiz on it just now. Chain rules in our past. The immediate thing we after we did implicit was we figured out the rule for natural log.
Yep.
Does anyone remember how we did that?
Where are you at? Well, I know what it is.
True, we know what the derivative is. Does anyone remember how we got it? We don't know what the hell the derivative of natural log was. We didn't before we figured it out. Can I rewrite that?
We use limit.
Yeah. So, real quick. Do you guys remember the formula for the area of a trapezoid? Okay, now watch. There's a point to this, and you're all like, "Come on, dude." All right. If I break it up into two triangles, I can then start to put those triangles because I know the area of a triangle, don't I? Do you guys see that it makes two triangles if I just drew better? Yes? If I just could draw better, maybe everybody would be happy. Two triangles, yes? Damn it, I almost got the mark. You guys kind of with me? So then it's the height and the base and the height and the base and the half, blah, 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 blah. And then you can put those together. So you took a form you didn't know and you broke it into something you knew. So here's a form we didn't know before.
But we did know.
But if I rework it, if I put it in a different form,
we know what e to the x.
yes, e to the y equals x. I can put it in exponential form. Now if I marry the fact that I know e, and we all love e, and we have implicit differentiation, bam, I can do that shit, right? What's the derivative of e to the stuff?
E
No
to
way.
stuff.
Times
Times
stuff
stuff.
prime. And what's the derivative of x?
1.
And then I divide by e to the y. Now some of you guys are like, that's not the derivative, but what was e to the y?
X.
X.
So 1 over X.
Yeah, cool. And just to remind you guys, if I put an absolute value in here, it would be the same derivative. It actually would match the domain. That'll become important when we do the opposite of derivative, which we'll do way later. So that's the way we started investigating like inverse tangent. I think that's the first one I did because it's the most common one we run into. So if I want to know inverse tangent's derivative, we do the same thing. How do I rewrite that? Yes, I can take the tangent of both sides. Because what does tangent do if you take it of inverse tangent? They
It cancels.
kill each other. They're like antimatter, right? So if I take tangent of both sides, they die. They kill each other. That's what they're built for.
Divide by tangent.
Hmm?
Yeah, so you gotta get the y on the one side, or is that it?
No,
so
that's
you got,
it.
got X.
Because now I know the derivative rule for tangent, and we know implicit differentiation.
Yeah.
So what's the derivative of tangent? Secant squared is something, right? Times
The
derivative of something. I'll do this side. Okay. So I get y prime is 1 over secant squared, and just to remind you guys, if I know x is tangent y, let's see if you guys are cool with this. Y is an angle, yes? Because it's inside of a tangent function, it must be an angle. Tangent is this side over this side. Yes? You guys remember this from pre-calculus or trig or whatever? If I have a definitive statement about a trig, I can create a right triangle, because that's fundamentally what trig functions are. It is ratios of sides of right triangles. And now I need to know what the secant is. To what side am I missing for that? Hypotenuse, and then we have old Greek dude, right? Actually, his followers that he took credit for, but that's all right. So this actually becomes 1 over the square root of 1 plus x squared. Is that cool? Because the secant would be hypotenuse over the x side. Is that all right? Okay, so that's the rule we got. That's the arc tangent, if you like, or the inverse tangent. Its derivative is this. So that's a rule we now know. Look at this white void I live in. So let me write it down up here. What's up?
Isn't it secant squared, so do we need to square it?
Oh yeah, I'm sorry. What am I thinking about? squared,
Square.
so it becomes 1 over 1 plus x squared. Thank you. So let me put it up here. So if I got inverse tangent, its derivative is 1 over 1 plus x squared. Okay. So I can do exactly the same thing. I mean exactly the same thing for all of the other trig functions. So I want you to do one of them. And then we'll just talk about what the rest of them probably must be. So what I want you to investigate, the same way we just did that one, I want you to investigate inverse sine. Okay. Do exactly what we just did. But this time for inverse sine.
Can you put the inverse tangent one after that? So we
Yep.
can follow the steps.
If you can make heads or tails of that. Yes. Inverse sine. Y equals inverse sine of x. So I want to know its derivative for y. So what's the very first step when you try to catch up to you guys?
Take the
Sine.
sine of both sides.
Okay, good. Just make sure everybody's got the right first step.
And you can take the derivative.
I could right now draw the triangle that I know I'm gonna need, right? So what side's the sine reference? Good. Y, the y side over that bias, 11. Much better than Sokoto. Sokoto sucks. And just in case I need it, what would this side be? 1 minus x squared. Is that cool? One of the hundreds is going to be subtracted in the other leg. What's the derivative of sine of something?
Cosine of something,
Times
the something.
something prime. That side. Y prime is 1 over cosine. Do we know what cosine is now?
Yeah.
Yeah.
What is it? Yeah, it'll be this over 1, yes? Yeah. So looks like for sine, arc sine, or inverse sine has got the square root staying inside. So let me write that down more concisely. If I give you inverse sine, its derivative is 1 over the square root of 1 minus x squared. Can somebody hazard a guess without doing much work? If I give you cosine, inverse cosine, what its derivative will be? What's the derivative of sine? X. What's the derivative of sine x? Cosine x. What's the derivative of cosine x? Negative sine x. So what's a decent guess as to what this thing's derivative would be?
Negative square root 1.
Yeah, that's it. That's the derivative for
Oh, okay.
inverse cosine. We know the derivative for tangent, inverse tangent, correct? 1 over 1 plus x squared. So what do you think the derivative of inverse cotangent is? Holy shit! Negative 1 over 1 plus x squared. So the same rule about the co-stuff's derivative is negative holds even if it's inverse. That's kind of nice. Maybe. Now, do you guys agree that secant and cosecant have two of the worst trig derivative rules? Maybe? It's not that bad once you get it, once you memorize it, but they each kind of like get bigger. Secant is secant tangent, and cosecant is negative cosecant cotangent, right? You guys kind of with me? So their inverse stuff are going to be the funkiest ones. So if I have inverse secant, its derivative is 1 over x square root of x squared minus 1. That looks exciting. And then if I have money and write it down, what would inverse cosecant's derivative be? Negative that. Yeah. Now real quick, let me ask you guys, what is the fundamental identity that sine and cosine are involved in? Sine squared x plus cosine squared x is 1. So isn't one of them squared equal to 1 minus the other one squared? Is that cool? Isn't that the form this stupid thing is in? 1 minus sine squared is what? Cosine squared. 1 minus cosine squared is sine squared. So I'm trying to help you out. The derivative for inverse sine and the derivative for inverse cosine both have the form of their freaking identities. 1 minus 1 squared is the other one. What about tangent and secant squared? You guys remember that one? Tangent squared theta plus 1 is secant squared. So what's secant squared then? Secant squared theta would equal, I'm sorry, what's tangent squared theta? It would be secant squared theta minus 1. And look what's in this guy's derivative, x squared minus 1. It looks like the form its identities in. Do you have to know what I just said about the identities? No, you don't. I'm just pointing out, that's kind of nifty. The form is in there. And if any of you are going to take Calc 2 in Chapter 7, those forms are stupid important, almost immediately. Okay, maybe. Okay. So just a bunch of more derivatives. I'll tell you this. I'm going to go ahead and do this for you. Okay. I'm only going to make you. You only have to memorize the inverse tangent because that's the one that happens the most. I'm not going to make you memorize the other ones. Inverse tangent just happens the most.
So then,
Yeah, you better say. You're welcome. Okay. So let's do this. Let's take a break. I'm gonna go get some copies of the handout we started working on last time. We haven't finished it. So we'll finish that handout, and then we'll see what else we're gonna do. So come back at like 10 after.
My brother is a sophomore. Because I bothered him about taking one class. He's still taking your other class.
All right, guys. So it's one thing to know the rule for a derivative. It's another thing to use it correctly.
Trying to understand how
So my earlier discussion about that limit sine x over x. If you look at the rule, I wrote the rule for us. That's the f part, right? The rule for inverse tangent is derivative. Can somebody tell me very specifically what's the angle in the function of the fx? What's the angle like? What's the angle? X. What does the derivative rule say it's going to do with that angle?
Square.
1 over 1 plus angle squared, correct? Isn't that what the rule says? Whatever the hell is in that arctangent, it's not an angle, I gotta be correct.
Yeah.
The output would be an angle, yeah. But I'm just trying, so whatever that measurement is, that x measurement, what will it do to it? It's gonna do 1 over 1 plus square of it. You stop. So let me really make sure you guys understand this. What's the derivative rule for e through this stuff? E to the stuff times derivative, right? You with me? What's the derivative rule for sine of stuff? Cosine. Okay. So every function has its own rule. Most functions just sort of leave the stuff alone. You see what I mean? Sine of stuff becomes cosine of stuff, and then times derivative of stuff. You with me? This sucker, it's the first function we really see where it says, okay, inverse tangent of stuff by itself. No chain rule. You with me? No chain rule. There's just x inside. It changes stuff. Now it's 1 over 1 plus stuff squared. I need you to see that. That's its rule. That's how its derivative works by itself. What's happening with g? Sorry. What's happening with g? What's going to help you out? Oh yeah, you got to get the right angle.
I'm doing it.
Sorry.
That'll be it.
Yeah,
That's good.
I got to find you a bigger table. Okay. What's the rule that's going to go on top of this guy's rule for its own derivative? What's the rule happening here? Chain rule for damn sure, right? It doesn't matter what this function is, there's a function inside of it. Okay, so the first level is just this guy's rule. And what is that guy's rule? What's it going to do to the measurement inside of it? What's it always
It's
do?
going to put it 1 over
1 over 1
1
that.
plus x squared
That
minus 4
Plus that one.
squared.
square. Good. Okay, we're not done yet because I haven't done
Times whatever the
chain
inside
rule
is.
yet. But this is the first function that works like this, and it makes sense. It's freaking inverse trig. Everything about it is probably weird. It's just weird by itself, right? But aren't we all? So that's what the inverse trig does on the first level, is whatever's in it, it does 1 over 1 plus it squared. Now I apply chain rule. What does chain rule say, of course?
That you have to
And what's
have
that?
the inside of
2x. So that's just the chain rule piece. The inside gets a turn, right? So then I can just write
So
that
it
as
would be
2x over.
1
And there's not a
plus x
damn
squared
reason right
minus
now to
4.
multiply that shit out in the bottom, yes? To your
Yeah.
When do I do it? Depends on what you're going to do next. And what am I going to do next on this problem? Nothing. So I'm not going to do a damn thing to it. Okay, maybe. If all I want is the derivative, you only have to do minimal simplification. All right. So every single trig rule kind of works like this. You with me? All the inverse trigs, sorry. They're the first kind of things where it does stuff. Just the rule itself does stuff to the inside. All right. Maybe. Okay. So coming back to this guy, does anyone need this handout still? Okay.
I think I need one because I left the old one I had.
Oh, let me make sure I got enough for people that need it. I gave you one today. Yeah, I got one.
You didn't do any.
Everybody else good?
So that's why I said like say.
Well, this is what someone gave me.
Okay. Okay. So all you do
All right, so we did 1A, 1B, and we did, I think that's it. Yeah, that's it.
So you're solving for what?
Sorry,
I'll see what came.
previous page.
Try it.
Oh, you
and
mean-
then,
What do you mean,
and
sorry?
then,
I'm not sure what I've done.
then after class, all.
I think oh, this year, sorry. I'm sorry, thanks for saying this. I forgot where I just was writing on. Okay, yes.
For 3B, did you mean geomet?
Yes, thank you. I'm not trying to be that tricky. I had a different equation there and then I changed it and I forgot to make this x here, yes. Okay.
Thank you.
That's a level of trickiness I'm not ready to cause you to deal with, okay? So let's try 1C.
I think after today, I think I've had mine a bit of crazy.
Yes, I understand. Does anyone know what 1C would look like if I graphed it?
Circle?
Anyone tell me anything about the circle? Would it be centered at the origin? No, it'd be shifted. Okay, that's all I want to know. It's a shifted circle. Yes? You could subtract the 2i, you can complete the square, you can figure out where the center is, and who cares? Okay. So I want to find dy dx, which we affectionately call y prime. So what do I have to do, of course?
Take the derivative.
It's crazy. So I'll get it started. There we go. I've done some stuff. Now you guys help me out.
2y.
Good. 2y, y prime, because the derivative of anything squared is 2 comes down in front of it to the first power and the second. Okay. This is just an application of chain rule. That's all that implicit really is. And what's the derivative of 2y? 2y prime. And what's the derivative of 3? 0. Okay, I like it. There's one thing that's in the wrong place to keep going. What's in the wrong place?
2y, y prime.
This little dude's in the wrong place. What's your problem? So I subtract that over, and then I can take out
Y prime.
y prime. And I can divide.
2 minus 2y.
So that's it right there.
2x over 2y.
Yes, sir.
Why didn't we add an additional y prime when we put the derivative on the right hand side of the equals sign? Like, yeah.
Oh, this here?
Yeah, like why?
It's
did
not
we-
an additional one. So real quick. Okay, this is a good thing. Guys, help me out. I'm sorry. Has everybody got that?
Almost.
I'm with you. All right, before I answer your question, Mercedes, if I wanted you to calculate the slope somewhere, what would I have to give you?
The slope. No.
The entire point, correct? I couldn't just say y equals 3. You're like, well, I gotta know what x is, dude. That's what the freaking thing needs. Okay. Now, this is kind of silly. You ready? This is really silly. Okay, y equals, I don't care, x squared. Take the derivative. What would you get? Tell me exactly what you get. Tell me the whole thing. What do you get?
Y equals.
Everybody agree that that's the derivative of the given thing. So the derivative of y is y prime. There's no question right there. You did it. So therefore, right here, what's the derivative of 2y? 2y prime. We know the derivative of y is y prime. We do that all the time, don't we? Isn't the derivative of y prime? We do it all the time.
It's 2 times y is 0, and then multiply that by y prime. So y is 0 is just 1, 2 times 1.
Sure. So you could look at it as if, what's the derivative of x would be 1 times the derivative of x is 1. What's the derivative of y? It's 1 times the derivative of y, which is y prime. A much better way to look at it, though, is just the fact that we know the derivative of y was y prime. This is what we've been writing since the beginning, almost. Okay, I like it. Okay, good. So all I wanted here was what dy dx is, but if I did ask you for the slope, I'd have to give you the entire point, and then you just plug the numbers in.
The slope and the tangent line, right? They're in both.
Sure, I could ask you for both. We got a tangent line problem coming up right now.
Yay.
Does anyone know what this shape is? No. Okay. It's a nifty shape. We'll just say that.
Sphere.
Nope. It's a good try. I like it. I like it.
Is it the butterfly?
No, it's not
No?
quite a butterfly. The butterfly equation has a little more to it. But okay, here we go. Can you guys take a moment and try to figure out y prime? Because again, just, if I ask you this question, why am I going to do y prime? Why do I need that?
Get the slope.
Get the slope. I love it. Brandon said that with the perfect intonation. Slope, Jeff. Good. That's the way I want you to be about it. It's old news. Of course I'm going to take the derivative. Okay. What's the derivative of y cubed?
3y squared.
3y squared y prime.
Good.
Oh, shoot.
How do I do the derivative of 7xy? What rule do I need to use?
Product.
Like
It's
y, x, y, and
So, derivative
Seven y plus
of
seven
7x
xy
is
plus y.
7 times y plus
Seven x.
derivative of y is
y prime.
y prime. So each piece gets its own term. I like it. Why don't I consider 7 prime? Because 7 prime will always be,
0.
so I don't even consider it. Yes.
Did you just do the chain rule quickly? I mean the product rule quickly?
Yeah, that's what we just did.
Uh,
Yeah. 7x times y. Derivative of 7x times y plus 7x times the derivative of y. That's the product rule, right? Product rule is each piece gets its own term, as the other guy just waits. Okay. Now what level am I on?
Now you just have to solve for y prime.
Beautiful. So if you underline your y primes, give yourself a little visual. You can go either way, but I always try to keep the negatives to a minimum, because negatives find a way to screw us over.
Subtract the 7y and add
Good.
the
I'm going to add this
3y
sucker over. So
squared
basically,
y
I'm just
prime.
going to switch these. Is that cool? I'm going to subtract 7y. I'm going to add this, so they basically just switch places. So I subtracted 7y, and I added 3y squared y prime. All I did. So now can I take a y prime out?
Mhm.
Are you guys cool with this? 3x squared minus 7y divided by, if I take a y prime out, what do I get? 7x plus 3y squared, so that's what I'm gonna divide by. Do you guys, do you guys see a symmetry between the top and the bottom on this problem? 3x squared minus 7y, 7x plus 3y squared. That happens a decent amount of time when you do implicit. It's kind of neat. Does it really change what we're doing? No, just want to point it out. Why did we just do this? I gotta find the slope so I get the equation. Okay, good. So I want to evaluate this at 4, 2, yes? So if you put a little line with the point at the bottom, that means I'm evaluating this expression at 4, 2. Is that all right? Yes.
Is that a subscript?
Yeah, it's like a little subscript, yes. A little 4, 2. Okay. So let's see if we can power through this. X is 4, yes?
Yes.
16 times 3 is 48. Y is 2. Minus 7y would be minus 14. X is 4. Y is 2. Is that okay? So I get 34 over 40, which is also known as 17 over 20. Does that look all right? You guys concur? Okay.
Yeah.
And that is the what again?
The
The
slope.
freaking slope check. Okay, I'm sorry. I just want to make sure. Always double check. As you do work, you will get to the point where like, okay, it's done. Why did I do that? So it's good to kind of check in. Why did I do that? I got a slope, yes.
So when is it when we have to just plug in 1 point? 'Cause
Oh, it completely depends on what this guy needs. How do I figure out y prime? I need x and y. If y prime was equal to 7y squared plus 3y over 2 minus y, I just need y, because that's all it needs. Yeah, so I don't have to know anything. I just look at the equation and say, what do you need, equation? So now I know the slope, I know the point, and now you can do whatever the hell you want to do to get the equation, right? You can do y minus y1 equals m times x minus x1. Y minus 2 equals 17/20 x minus 17 over 5. Is that cool? The 4 and the 20? When you multiply it through? Yes? Alright, you guys are good there. And then I add 2. If I add 2, I'm actually adding how many fifths? 10 fifths, so then I get minus 7 fifths.
Can you do that?
Yes. Move it a little bit too. So this was the work just to get the slope. I already had a point, so then I could put the equation together pretty easily. This is just one notch up from algebra. We just have a different way to get a slope now. Algebra would look at this problem and scream. And then go take a nap. I don't know. Would have a rough time. Okay. Some of you guys are like, that's exactly what I would do, John. Alright.
Okay, it's y2 minus y1.
Yeah, well, this is y minus y1 equals n times x minus x1, yeah.
Okay.
Or you could use mx plus b. I could have done the mx plus b and plugged in what I knew and solved for b, right? You could do it either way. Either way. I'm gonna kind of keep this alive a little bit because there's a section where that's gonna come back in a big way. So I just want you to remember the y minus y1 thing, but you can do mx plus b. I don't care. Okay. Now, let me ask you, let's do, okay. What's this guy's derivative here? This isn't that bad, right? Natural log, how do you guys feel about natural log? What's his rule? His rule is relatively beautiful, right? Because what does it
1
always
over
do?
x.
Yeah, 1 over
1 over x squared minus 7x.
times,
2
yeah, let me go ahead and write it all out.
minus 7.
So it'll be 2x minus 7 over x squared minus 7x. Is that all right? The book writes it as g prime of x over g of x, which is dumb, because it's not a new rule, it's just chain rule. So I always don't like it when a book makes it seem as if it's a new thing. No, it's just chain rule, that's all it is. Yes?
So for the x squared minus 7x, is that also a separate chain rule too?
Sorry?
Like for the x squared minus 7x, is that like a separate chain rule as well? So like would you do x?
No, this is the only chain rule. So there's one function with one function inside of it. So the derivative of the outside function is 1 over stuff, and then the stuff gets a term, yeah. So it's not like a double nested doll, right? Okay, and then we get this guy. Let me make it so you can see what it says. There we go. This should be an x, yes. Okay. What's the rule, just right up here, what's the rule for inverse sine of x? It's bad enough already.
1 over square root 1 minus x.
Good. Remember, cosine's an asshole, so his derivative has a negative.
Cause he's negative.
There you go. So, whatever this is, gets put right there and gets squared, right? That's the rule for sine, that's inverse sine. That's not even considering chain rule, so I'm gonna have to do a chain rule here, correct?
Mm-hmm.
But the first level is just, what does this guy need to happen? So when I take a derivative of inverse sine, it becomes
1 over square root 1 minus
stuff
squared
squared.
minus 1.
I'm not done. But that's just doing what inverse sine needs to happen. Yes? That's his rule. Whatever is inside of inverse sine gets shoved right there. What have I not done yet?
That's
Times
prime.
stuff prime. So what's the derivative of e to the x squared?
E to the x squared.
Oops, sorry, times. Yeah, e to the x squared times, which is, I'm sorry, 2x. And of course the derivative of negative 1 is 0, so that part goes away. Okay. So you could write 2x e to the x squared over this business. Is that cool? So inverse trig functions, not surprisingly, have very complicated derivative rules. That's not surprising because they're weird in the first place. So of course they're going to have kind of gross derivatives. Maybe. What's the only one you have to memorize for me?
Tangent.
Inverse tangent, yes. That's the one that happens the most. If you know inverse tangent's derivative rule, you'll do really good in some parts of the next part of this, and if you take Calc 2, you'll be ready for a lot of things that happen there. Yeah?
How would you write the answer again?
I'm sorry, so you would make it 2x e to the x squared over the square root of 1 minus stuff squared. Please, dear God, don't boil this out. There's no point to it. Yes? Just put all that crap. Isn't that all that crap over 1? So can you just throw it on top? Yes?
So, when it comes to memorizing things, do you also need to memorize sine and cosine inversions too?
What do you guys think?
No.
What's the only one you have to memorize? Inverse tangent. Okay.
I mean, it might be a good idea, but.
Might be a good
I
idea.
don't want to. At this point.
Okay, that's up to you. Alright, so last thing. So let me say this. I think you guys will be very cool with this. We're not going to have section 3.9 on this test.
Yay!
Ain't no way in hell I'm going to try to get into 3.9 with that much time left. Just to say this. 3.9 is our first look at calculus type word problems.
Oh, I.
You know what's coming. I mean, come on. Every math teacher, we're like, we're finally getting the word problem section, everybody's favorite. It's so freaking cool though, guys. Please give it a chance. I shouldn't even have said that, but you know.
I gave it a chance before and I did not like it.
I understand. Alright. That's just one person. It's like one bad yellow. Out of a billion.
That's all it takes.
So 3.9 will do, and then of course the rest of 3 will do, but this test will go up through 3.7. So in the time I have left, we're going to talk about 3.7. Has anyone looked at the homework for 3.7? Like, how much homework from 3.7 did I assign?
Like 5
Holy shit. 4 problems. I think it is right. It's like 4. It's okay. On the order of 5 problems. Okay.
Does that mean even the homework, we only do it for 3/7?
Yes. Cool. Now you can go more than that if you want to. It's fine. How do you really feel? All right, so let's talk about the one thing. Now, the unfortunate thing is, not really unfortunate, in the interest of time, I know from looking at the survey you guys filled out, some of you guys filled out, some of you guys are looking to be engineers in the future. I think some of you guys are going into medical fields possibly. Yeah. There's a section 3.7 is how calculus is used in a lot of the different natural sciences. The one piece of it I'm going to focus on, because I always know I never have enough time to go over everything in 3.7, is what's called kinematic formulas, which are like position, velocity, acceleration. These are things we have experience with. I'm not going to do Newton's law of cooling. I'm not going to do it. But they are in there. I'm very sorry. So let's talk about how kinematic stuff works. So very often what we're given, and of course math people being the normal people that we are, we said, okay, we have a position function, a function that represents position. Let's use the letter S. Yes?
This is section 10.7.
3.7. So just deal with it. That's the way it is. So when you see S of t, that means a position at a time. Yeah. So if I throw a ball up in the air, it could be governed by this formula. We're going to make it actually kind of correspond to real life.
4.9.
The units I'm using, by the way, are meters and seconds. Like most of the rest of the world uses.
4.9.
Yeah. So just so you know, if I throw something up in the air, doesn't it eventually stop for just a millisecond and then it starts to come back down? Not even a millisecond, but you guys get my point. And why does it do that? Gravity. It's always acting, so if I throw it, I give it some velocity. And when I release it, it immediately starts to lose it. Because Earth is going, right? So then it reaches a point where the velocity is 0, and then it turns back, right? Because now the acceleration, so when it's first going up, is the movement in the same direction as the acceleration? If it was, it would just go faster up. That'd be weird. We just jump and we fly up into space. That would be bad for humanity. Right? So thankfully acceleration is acting this way, so that's why it slows down, and now it's moving in the same direction as acceleration, which is why it starts to speed up. So this is a very strange concept for some people. If I'm in a car and I'm moving forward, and then I press on my brake, is my velocity acting in the same direction as my acceleration?
No.
If it was, I would speed up. My acceleration is acting backwards, which is why it's taken away from my velocity, and then eventually I stop. Unless you had my old Dodge Charger, in which case you don't quite stop it.
Oh no.
Shit. Sorry. Eventually the brakes were like, I'm done. Alright. Okay. So that's just some kind of basic stuff. How do I get, so this is the position. So if I just said, where is the ball after 1 second? How would you figure that out? So I'm throwing this ball in the air, where's the ball after 1 second?
Plug
1.
1 in for T.
1 second? Yeah, you would just plug a 1 in for T. So 40 minus 4.9. So 35.1 meters up in the air, right? Everybody with me? That's awesome. So if I ask you a question about the velocity now, and I'm going to ask you about the acceleration, how is the velocity related to the position? Yeah, because isn't velocity a rate of change of position? And we know now that's just another name for slope, which is another name for derivative. So what is the velocity formula? Let's put it up here. Bless you. You really want to start using words right now, Jeff? Sure, man.
First derivative of
That
derivative
would
of the
be,
position.
Yes.
40 minus,
Good. So that's my position.
yeah.
What's my acceleration? What's the acceleration function?
That's
Yes.
Derivative
So
of that,
third
second derivative.
velocity is
That's
like
the third
miles
derivative.
per hour for most normal Americans, and for a
So
lot of the rest of the world,
it's
it's meters per
9.8.
second or kilometers per second. This is meters per second, and then acceleration is going to be how quickly velocity is changing. So it's like meters per second per second. Over time, how does the velocity change? So we actually say it's meters per second squared, and then students go, what the shit is a square second? Well, I can look up the cost of time. I don't know what you heard. So acceleration would be what?
9.8.
Negative 9.8.
9.8.
On the Earth, that's the number on most of the Earth. It varies a little bit, but it's 9.8 meters per second squared is the acceleration depth. If you're standing between two mountains, you actually weigh a little less because the mountains are pulling you up a little bit. So your acceleration is a little less between two mountains, right? So you just live between two mountains. So if I ask you what's the velocity after 2 seconds, what would you do? Holy shit, plug it in. So, yeah. So you do velocity at 2 would be what?
8, 9, hold on.
Yeah, what'd you get? 21.4? 20. Yeah, 20.4, yes, okay. I'll have to catch up to you. 20.4 watts?
Meters per second.
Meters per second. What will happen eventually to the velocity? Do this ball in the air.
It's gonna come down, it's gonna
It's gonna
be
become
negative.
0, and then it's gonna become
It's gonna become negative.
negative. So of course, negative velocity, so speed has to always be positive. Velocity can be negative because it's when it's positive, it's going up, when it's negative, it's going down. Is everybody with me? So a lot of the problems in this section, they'll give you a position function. If I were you, I would immediately take a couple derivatives, and they can answer any freaking little question they ask you. Yes? What's the acceleration at 3 seconds? So just plug a 3 in the acceleration thing, right? So what's the acceleration after 3 seconds? Sorry. Well, for this problem, what's the acceleration at any time?
Negative 9.8.
Because we're on the Earth, and that's the acceleration we always experience, right? Okay, I like it. If I'm talking about a train, its acceleration is dependent on what they set the engine to. Doesn't have anything to do with 9.8 necessarily, so its acceleration could be changing over time. Do you guys know, anybody know what the, so the first derivative of position is velocity, the second derivative is acceleration. Anybody know what the third derivative is? And this is like my old Dodge Charger. So I would hit the acceleration, the accelerator, and it would go. So what would you say that motion is? That motion.
rate of change.
Was it
Jerky.
jerky? There you go. It's called the jerk, believe it or not. So the
What a
first
jerk.
derivative of velocity, second derivative of acceleration. The measure of how the acceleration is changing is called the jerk, and that is a perfect name for
What
it.
a jerk.
Because that's if your car's jerking, that's.
So how would you get that one? So it would just be 0 for this.
Yeah, for us, we have a smooth. There's nothing that's causing this to jerk around, right? If I had some like strong winds, I might have a different acceleration. You guys got
So
with me?
if like
Yes.
if the 4.9 was originally 4.9 t cubed.
Yes.
And then,
Good. If I have a higher power on my original position function, which could be true because of wind. It could be true because I'm on a train and I got the engine set to some weird alternating thing. Are you guys kind of with me? I love you guys. Some of you guys look very concerned. Yes.
So then what would the I guess notation be for that? Like we have S of t, V of t.
Oh, don't
A of
worry
t.
about the jerk. It's not going to come into play. I just want to let you know it
Okay.
exists and the name makes sense. Yes.
Did the Dodge Charger give you a headache?
In many ways, yes.
What was SFT again?
What's S of T? Position.
Position.
So we said, what's the third letter? S. Okay, let's use this.
So
Yes.
it goes from position to the derivative of that velocity.
Velocity.
Derivative of that.
Acceleration. And if you just think to yourself, if my position changes, that's how quickly I'm moving. If my velocity changes, that's how quickly I'm accelerating, right? So that's why it kind of makes sense. Every step of a derivative gets me to the next. How quickly is this changing? Oh, no, not by itself. It could indicate the no, understood.
This position.
I know what you're thinking, but it's not quite. Okay. So now I forgot what it was. Okay. So what if I ask you this kind of question? What is the velocity when it hits the ground? Right before it hits the ground. Now, if you say when it hits the ground, you're like,
Zero.
I was waiting for Mike to come in. What is the velocity right before it hits the ground?
You do a limit.
So that's zero?
You would have to do a limit, right?
A limit?
It's approaching zero.
The limit as it approaches 0.
I love the way you're thinking. Not that much shit.
Oh,
Velocity
okay.
be almost that to gravity?
Not my, sorry?
Wouldn't it be almost that of what gravity is?
No. I'm sorry, say that again. I'm sorry, why?
Or wouldn't it be close to what gravity is? The velocity of gravity?
Oh, no. So look at the original function. Can somebody tell me at what time the height is 0? There's an immediate easy one.
Zero.
When, at the beginning, so somehow, this problem is kind of funny, because I am laying on the ground, maybe I just caught a ball playing baseball, and I kind of like threw it from the ground. Are you with me?
4.9?
Threw it from the ground like a little. You guys kind of with me? Okay. So at the beginning, when t equals 0, it's on the ground. And I'm under the ground. I'm like,
In a missile silo.
okay. Now, okay. When else? Isn't there another time when it's 0? Because what can I do with this stupid thing?
At your highest height.
Factor. So what am I doing right now? It's asking me velocity right before it hits the ground. Well, the only thing I can do to get velocity, what do I have to know to get a velocity? I have to know a freaking time.
Yeah.
So right now I'm just saying, how much time would it take for it to almost hit the ground? And then I can just plug that damn thing in. You see how you can get relatively easy problems to figure out that are multi-steps. What's the velocity? I could have said 3 seconds before it hits the ground. Then you figure out if t is 7, then you subtract 3 from that, and then you plug 4 in it. So I can do. Question. So what do you get when you plug it? Take a t out.
40.
And if you solve that for set equal to 0, you'll get 40 divided by 4.9, which is something. Sure. Okay. So about 8.16. And then how would I answer the question I just asked? Plug 8.16 into that. The velocity function, right? Or the first derivative of the position. You guys with me? What do you get for, I'm sorry, go ahead. What do you get for that? Sorry, you okay? Okay.
Negative 4.
Sort of? Okay. I want you guys to really with me. When does it hit the ground? When the height is 0. When the position above the ground is 0. Yes? It was 0 at the beginning. It was also 0 at 8.16. So I threw it from the ground, it went up, and then it hit the ground like, thankfully, a lot of things. Right? The question was, what's the velocity? Now I know when it's almost going to hit the ground, I can just throw that in. I love that you guys were worried about limits. I don't need a limit. Right at 8.16 seconds, it hits the ground. So if I just plug that in, it'll tell me what the velocity is. When does this equation stop working? When it hits the ground.
When
Yes.
it's negative.
So I don't need a
When
limit.
it
I can
tries
just
to
plug
go
it in.
negative.
It's not at the vertex?
What do you mean? Sorry. No, the velocity is not, doesn't stop working when it's here. That function stops working when it hits the ground, correct? When that ball hits the ground, is it going to continue?
I hope not.
Jesus, now I think it's like a phantasm thing. And it drills into the ground. I don't want to play that
Depends on what
game.
the ball's made of.
Don't want to play that game. Don't want to catch that ball.
You go down with it.
So what do you guys get when you plug in 8.16? I just want you to get 4. What do you get?
Virtual mass.
49 minus 9.8 times 8.16. Negative? Negative? Yes, it should be about negative 40. Is that what you said? I'm sorry, I thought you said negative 40. Negative 39 point whatever, right? Which makes sense because it's going down. So it should have a negative velocity.
I got negative 44.28.
I want to know right before it hits the ground, how much time does it take until that happens? Well, it's either at the beginning is when it's on the ground, but I want it right before it hits the ground. So that's the other place where position is 0. So it starts on the ground, I throw it. How long until it's the ground? Well, I just make the position, the height above the ground, and make it equal to 0. And then we solve it. So we factored it.
40 divided by 4.
And then if I do 40 minus 4.9 equals 0, I'll get 8.16. I just get what makes it 0. Right? Okay, yes.
So this, when you put it equal to 0 and factored out and whatnot, that is what happens, or how we would go about if the problem says, like, what is it when it's at ground level or whatever.
Oh, what is it? Well, when
when it's at the ground, or like when it's at the end of its cycle or whatever.
yeah, I'll just say when it hits the ground. That's the best way for it to say it. I'm pretty sure most of the problems say that. Oh,
Or if you threw something on
this
the
would
building.
still work. It's a beautiful question. What if it was
Ground
water
would be
that it was
different.
going into? Would that velocity function stay the same? No.
No.
Why not?
Because it can become negative.
Well,
If
because
it
now I'm
sinks.
going through a different medium, and therefore I'm going to have something pushing back against me, like velocity goes. But the answer would be exactly the same. What's the velocity right before it hits the water? It would have the exact same question. Because right after that, for our problem, the velocity function stops working. If it was water, and that's how I say water, it would continue moving, but that velocity function still wouldn't work. But I would still plug 8.16, I'd still be golden. Because right up until that point, that works. So guys, I just want to point this out. Number 4 is the problem that's just like this.
Okay.
And if you give me a second, I'll tell you which problems not to worry about in number 5 because they're related to section 3.9. Also, can you guys do me this favor? It's page, do you see where it says page 267 on number 5?
Is that wrong?
It's page 270. Good old faithful Jeff. 270. And I think it's numbers, get your freaking glasses, Jeff. Oh man.
825, 70, 74, 89,
What number is it?
101.
105 is a related rate, so don't worry about that yet. 101 is a related rate, so don't worry about that yet. and you'll be very happy to know that the rest of them, you have to do.
Oh,
You don't have to, it's practice.
okay, and this,
101 and 105, you don't have to worry about yet.
and this test is 3-1 through 3-7, right?
This test is 2-8
Oh,
through 3-7.
Can I see a picture of the first problem I missed from the last class? Of the 5 worksheet that I missed